new, and our final new speaker, Immanuel Bloch, who's from Munich, LMU, Max Planck Institute.
All right. Yeah. Thanks a lot, Matthew. Thanks for the invitation, and a pleasure to be here. So I heard you had exciting weeks, very dense weeks, a lot of information. So I'll try to lighten things up a bit. I'm a humble experimentalist, so I'll not try to make very complicated, sophisticated derivations, but still, I'd like to work mostly on the blackboard and try to, give you intuitive explanations about several phenomena, which I think are important. Try to introduce you to the field of quantum simulation with ultra-cold atoms. And so I picked just a few topics. The point was not, I thought, well, there's no point in throwing 200 slides at you in these 3 lectures, but let's just pick a few things that I think are interesting over the past years, that have been quite interesting, that I think help to understand what we're doing, why we're doing, what the new capabilities are that we can have in these systems. And so I just picked a few topics. There could have been many other topics we could have chosen, but of course, for this course, this is my choice. If you have anything else you think would be exciting to talk about, that you know about, just let me know. I mean, I can prepare for it in the evening. We can discuss it in the next 2 lectures, So I'd like to start out with telling you a little bit about the system. You probably heard already a little bit on the Rydberg systems already. I want to expand a little bit on that, on the AMO systems, tell you what we can do in these systems. So that will be mostly today. And in the lecture tomorrow, I'd like to talk about driven quantum systems, driven quantum matter, mostly Floquet systems, tell you how we can realize new topological systems with them, which have no analog to kind of standard classical topological systems. And I'll introduce this topic of quantum gas microscopy, which allows us to really have the single particle detection and manipulation in these systems that brings like a lot of fruitful new capabilities. And we'll apply that to a few things. And one actually very nice example of how you can what you can do with that is, for example, look at spin charge fractionalization, and we'll talk about what that is and how you can measure that with these new tools, and why that gives you really a lot more insights than what you can normally do in the condensed matter experiments. And then in the 3rd lecture, I'd like to switch mostly to even more to the out of equilibrium dynamics. So we'll talk about NBL experiments, thermalization experiments, how to measure entanglement entropy in a kind of Hambry-Brown twist generalization to many-body level, and then talk about how we can have new ways of measuring quantum transport by really being able to measure the full counting statistics in these systems. Okay, so that's what I want to talk about, give you a little bit intuition about. And is that okay for you? You're happy with that? Anything we should talk about more? Just let me know. And yeah, I hope it's going to be interactive. Really, if we don't make it for everything, absolutely no problem. You'll get all the notes, all the slides, so you get everything. You can study it afterwards. It's really much more important that we have an interactive, good time here, that you ask questions, that you understand what I'm telling you, or I know when you're not following or not understanding things, you have questions about something. So really interrupt me whenever where you want, where you feel like it's a good time to interrupt and to discuss. So yeah, so what we want to talk about are ultra-cold atoms, mostly, although it applies a lot what I'm going to talk about to molecules also. And you've probably already heard there are quite a few different ways how we can look at the interactions of these ultra-cold atoms. I'll talk about trapping in a second, how we can confine them. And we basically have a few different ways of having them interact, either through direct collisions, which I'll talk about in a second. Then we have dipolar interactions, both, for example, by using magnetic atoms or molecules, which could have a polar dipole moment, electric dipole moment, or we have these Rydberg atoms you heard about, which we're also going to talk about in a second. And then there's this other field I'm not going to talk about, which is super interesting as well, is when you put these atoms in a cavity and basically can realize all-to-all interactions by passing the light to the atoms. And when the atom interacts with this atom, it picks up some phase shift, and then it imprints that on the next atom. So with that, you can see that you can generate like an all-to-all interaction in that system. So let's start and talk about interactions and potentials. So first thing I want to talk is interactions and potentials that we have for quantum simulations. And the first interaction we want to talk about is this collisional interaction. really what we're thinking about is like two atoms that approach each other. You know, they come close to each other. The electron clouds start to overlap, and they scatter off each other. For example, it's got a scattering event. We have the outgoing atoms, and that constitutes the scattering process. We can use scattering to solve the scattering potential, where we scatter the atoms from. And we, of course, also know that for bosons, we need a symmetric wave function, whereas for fermions, the two-particle wave function needs to be antisymmetric. The potential these atoms scatter off, you also all know, that's basically just a Born-Oppenheimer potential. You know, when these atoms get close, the electron clouds overlap. It's basically like a molecule forming. So the scattering potential as a function of the internuclear distance between the atoms, with just something like this. Oppenheimer potential with the different vibrational levels, rotational levels. This we'll see in the long range is given by a C6 divided by R to 6 van der Waals potential. Actually, we'll see where that comes from. We'll derive it again in the context of Rydberg atoms, but actually it appears also here in a very general context. So this is, and this can be rather complex object, right? This is a complex object when we study that, but it turns out the nice thing, if you're in the ultra-cold regime, and this is something you've probably experienced also, you know, when you see water waves hitting a pond, a stone in a pond. Let's say you have a water wave which hits a stone in a pond. If the wavelength, if we want to resolve the features of this stone, then we have to have a wavelength which is comparable or shorter to the features of the stone, right? Otherwise, we just can't resolve it. And if we're in the ultra-cold regime, by definition, this means we're in an extremely long de Broglie wavelength regime of matter, right? Ultra-cold means very long de Broglie wavelength. So we basically are in a regime where this wavelength is extremely long compared to any kind of features of the scattering potential. And it turns out, and you can do that, then the only thing that you're going to see is outgoing spherical wave. There's just a spherical wave going out. And there's just one thing that determines there's a strength of this spherical wave that goes out in the phase of this spherical wave that goes out relative to the incoming wave that basically determines, can effectively describe the same scattering process as this complex potential does. And that basically gives you the intuition why there is something, we can replace this complex scattering potential by a so-called pseudo-potential, which is just this delta function, where the entire scattering process is captured by this scattering length in this ultra-cold regime, which tells you how strong the scattering is, right? Okay, so that's the intuition why this works. When the long wavelength regime, there's this one number that determines all the scattering, and scattering off this stone is like scattering from a delta function perturbation with the right strength, okay? That's why this works. Now, interestingly, this A, although the potential here is always a, this A can be both negative and positive, because this tells you about the phase shift of the incoming to the outgoing wave. So the pseudo potential that we have here between the two particles can basically be repulsive or attractive, and that depends now on the details of the scattering process. Now, the nice thing with this scattering length is that we can tune this with the magnetic field in atomic physics, and this is what we call a Feshbach resonance. What is this Feshbach resonance? Do we have a stick somewhere? Is there, or a pointer? Or no, a stick. Is there a classic, just a stick? Yeah, but just a, is there a stick or just a something? I want something mechanical. There's more. Okay. Anyway, so so there's what we call a Feshbach resonance, and the idea is the following: imagine now with applying a B field, you can grab hold of the tail of this Born-Oppenheimer potential curve and move it up and down. And if you can move this Born-Oppenheimer potential up and down, you can control whether this last bound state here is close to threshold or above threshold, is gone beyond threshold. So you can really tune this depth such that you find a bound state very close to zero energy. Okay, when that occurs, you have a resonance scattering process. Because your energy of the incoming particles is close to zero, you have a bound state close to zero energy. And that's, of course, when you have the incoming energy resonant with your object, with the energy levels of your object, you always have resonance scattering. And that's what this is about. So this B is the tuning knob for tuning the bound state, tunes the bound state and the potential, and allows us to change A as a function of B. So typically this looks like this. And we're not going to derive this. I just give you what this looks like. So this would look, for example, like this. This is the scattering length. This is the B field. Here, obviously, we have this resonance that I told you about, where this scattering length diverges. And then we can have these special cases where A can be zero. Then we're realizing it's like having refracting particles. Although there is a scattering potential, there is a molecular potential, these particles scatter off, it's like they would see nothing. Then there can be cases where we have A smaller than zero. It's like having an attractive potential, attractive interactions, or A very large, positive, repulsive potential. Okay, and that's very nice because this allows you, with this knob of the magnetic field, to tune the interaction potential between the atoms very nicely. Okay, that's very nice. We're going to use that a lot, as you're going to see. If you want to, there's a very nice review by Cheng Chin and colleagues on this in Rev Mod 50 from 2010, where this has been extensively in the community. This depends very much on the atom. This can be at very low fields of a few Gauss. And for other atoms, it's at very inconvenient fields of thousands of Gauss. And then we are not so happy as experimentalists. And typically, we want this also to be rather broad, so we don't have to tune the field so precisely. Yeah, I should actually write down the formula. So let me see, I have it here. So this A of B is just the background scattering length times 1 plus the width of the resonance, B minus B naught. So that's how you can most parameterize most of those resonances. This is the width of the resonance. This is the background scattering length when you're far away from resonance. And yeah. All right, so that's what you should know. We can tune the scattering length, the interaction potential through this Feshbach resonance. All right. Please, sorry, yes. That's just a parameter that characterizes how broad this resonance is, how wide this resonance is. B naught characterizes the position of the resonance. At what field does the resonance occur? And again, that you have to do atomic physics calculations to predict that, to calculate that. It's no general formula on this. Okay. All right, good. Okay, that's what you, for now, need to know about interactions. Let's talk about trapping. How we create these optical trapping potentials. And it really always, in light atom interaction, there's these two formulas you need to know on atomic physics, minus d dot E and minus mu dot B. Then from there, you can follow, almost everything follows magnetic trapping, optical trapping, almost everything. So this is, of course, a light atom interaction, where we just have the interaction Hamiltonian. We have the dipole moment inside an atom, expressed by the dipole operator. And here I'm treating the field semi-classically. So I'm thinking about the field as a classical field. Nothing quantum yet. We could quantize the field, but I don't want to do that here. We don't need it. So it's like a classical field, classical coherent field interacting with the object, a two-level system. And now when you shine light onto your atom, when you shine this electromagnetic wave onto your atom, which has the electron here, what this does, it basically makes the electron oscillate. So it basically induces a dipole inside the atom. Okay, so we can calculate all that from the interaction Hamiltonian two-level system. But what we just need to know now is that we're going to get a dipole moment inside the atom, which is proportional to the applied electric field, and the proportionality constant is the polarizability of the atom. Again, something we need to calculate from atomic physics, which tells us how strong the dipole moment is when you apply a field. Okay, So if the electron is more tight bound, you will have a low polarizability. If you talk about Rydberg atoms where the electron is very far away from the core, then this is super high polarizability, of course, right? What can we say? So let's plug this in here, and now you understand immediately optical trapping. If we plug that in here, we find that the interaction energy is basically the polarizability is a minus sign here, and the minus here, minus alpha of omega norm E of t squared. And remember, a norm of E of t squared, that's just proportional to the intensity of the light field. So this is just norm alpha of omega, I of omega, where I is the intensity of my laser beam that I'm shining onto the atom. So we have a potential which is proportional to the intensity of my laser field. And whether it's attractive or repulsive depends on the sign of alpha, right? Because that positive would make this negative, an attractive potential. If alpha is negative, it would be repulsive. Or if we go back to this formula, it basically means the dipole oscillates in phase with the electric field. The potential is attractive. If the dipole is 180 degrees out of phase with the applied electric field, you have a repulsive potential. All right? Very good. So, but you all know, now it doesn't matter whether we talk, an atom is just like another resonance object. We all know what the phase shift, when you go back to classical mechanics and you just ask, you drive a resonance circuit, mechanical resonance circuit, and you ask the phase shift versus drive frequency. If you have a resonance frequency, let's say in our case, the two-level resonance frequency omega 2,1, what is that? You all know that. It's always the same story. How does that look like? No, that's not a Laurentian. It's the phase response. It's not the amplitude response.
Low frequency in phase.
Absolutely correct. And on resonance? Correct. That's very intuitive also. You think of it, you have a ring with a mass attached to it in your hand. That's a resonant circuit, right? And you drive it very slowly. Then obviously the mass is just going to follow exactly what you do, so it's in phase. However, if you wiggle much faster than resonance frequency, you will find that it's 180 degrees out of phase. So this is like something like this. Pi 0, and on resonance, pi over 2, right? Okay, very good. And the width, of course, is now determined by the line width of the resonance. In our case, the decay rate of the atom. Okay. And now you immediately know how we can trap atoms. If we want the dipole to oscillate in phase between the light atom, we should be in a regime where the light field is below the resonance frequency. This is what we call red detuning, because the frequency of the light is smaller than the resonance frequency. If the frequency of the light is larger than omega 2,1, we're blue detuned, and then we have a repulsive potential because the dipole oscillates out of phase with E, and we have a minus sign here, so you get a repulsive potential. All right? That's all you need to know, and it's also very intuitive. We can just derive that from the two-level atom also. And what we find, if we think about Rabi frequencies that we introduce, we find that the dipole potential we get is just h bar norm omega squared divided by 4 times delta. If we do the two-level system calculation, where I'm now thinking about a two-level system with levels G and E, they're coupled here with they have some resonance frequency omega EG. We have light here, which has a Rabi frequency, couples the ground state to the excited state with h bar omega Rabi frequency, and there's a detuning h bar delta between those two states. Sorry, small delta. Oh, you brought a macroscopic stick. Very good. Thank you so much. I take this one. All right, so you have the h bar delta here, and that's what it is in the two. And you can just derive this. This actually follows very generally from your just two-level system. If you diagonalize the eigenstates and you go to the limit where the detuning is larger versus to the Rabi frequency, you immediately find this dipole potential, but you also see for red detuning, so delta is the light laser frequency. Oh, wow, we're getting even better, I guess. Like, all right, omega EG. Yeah, this one was more like sharp edges. Very good. I don't want to get sued. I want to live here on Saturday without being sued by anyone. All right, good. Okay, great. So now you understand how we can create optical traps. We can, for example, just take a laser beam, send it through a lens, focus it, And if we're red attuned, that's good. Then in the intensity maximum here, we'll have a potential minima for the atoms. So we can trap atoms in the focus of this light field for red detuning. Okay. Red detune, and this is what we call an optical dipole trap. Note that it's a conservative trapping potential, so we can't cool with this. So we have to find other ways how to cool, but I'm not going to talk about that in this lecture. That will go too far. There's a whole lecture on laser cooling, how you do that, Raman cooling, sideband cooling. Also, again, always the same story. Doesn't matter so much whether you work with atoms, ions, or superconducting systems. I mean, I think it's always the same story. All right, so that's that. One thing we're going to look about a lot also is these optical lattices, where you can take, for example, two laser beams, counter-propagating beams, form a standing wave, and this standing wave has wave now separation lambda over 2 if you do 180-degree interference. And then locally, we can think of these as harmonic oscillators. And we actually really want these traps to be very closely spaced, because what we want, in contrast to the Rydberg tweezers, we want the atoms to tunnel from one side to the next. So we want close spacing. Remember, tunnel coupling depends exponentially on the distance or on the depth of this potential. So we want them to be very closely spaced for the physics we want. And here in the local on-site wave function, we can characterize by the so-called Wannier wave function, which for our purposes is just good enough to think of it as a Gaussian ground state function of your approximate harmonic oscillator that you have. All right. You all with me? Any questions? You shout, right? If I'm going too slow, you tell me. If I'm going too fast, the only way to slow me down is to ask questions. All right, so you have to then just Zeno effect me and just stop me. And but yes, please, yes. This one, omega EG, that's just the difference, that's the resonance frequency between the ground and excited state of your two-level system. And we think of the atom as just an approximate two-level system. Okay, great. All right. So we have interactions, the pseudopotential, we have trapping, and now we can already make the next big step and go to our Hubbard models that we're going to use as one basis for studying quantum dynamics. And the starting point is just to start from the many-body quantized Hamiltonian. Let me just write it down again once. So we have the field operator, which destroys a particle at position r, the kinetic energy term, the external trapping potential, which could be the optical lattice or the dipole trap in our case, psi of r, d3r. Plus, and then comes the interaction part, of course, psi dagger, r, r prime, v of r minus r prime, psi hat of r, psi hat of r prime, right, d3r prime. All right, that's the general many-body Hamiltonian. And now we can, if we're working in lattices, we can do two things. We can say, okay, how can we write this field operator that destroys a particle at position r? Well, that can be basically, if I write it in terms of destroying a particle on lattice side I, that would be basically the sum of destroying the particle on side I weighted with the amplitude of the wave function having an amplitude at position r. So even 100 sites away from that position r where I don't want to destroy a particle, I have a non-negligible, non-zero amplitude that this particle could have come from a very far away lattice site. But it's going to be low, of course, right? So we put in here, and we put the pseudo-potential approximation. One moment, we just make the step. We put the pseudo-potential in for V of r. That immediately gives us the Hubbard Hamiltonians. That's it. So that then we arrive immediately. Let me just write those down for bosons. For Hubbard Hamiltonian, we have minus T Pi dagger Bj with next neighbors. Sorry, did I make them write a bit bigger? Okay. Then I can get less on the. Okay, minus T bi dagger bj. Is it really so bad?
From that corner.
Yeah, okay. I'll come back to your corner in a second. Okay, I'll try to be better. So 1/2 U Ni minus 1, or for fermions, and if we have two spin components for fermions, we can have the sum over all neighboring lattice sites, Ci dagger sigma Cj sigma. So sigma indicates the spin of the particle, can have spin up or spin down. Here I'm not taking spin into account, I'm just thinking about spinless bosons. So this is just the hopping, the tunneling, which comes from this first term here. And then there's the interaction term plus U, and then Ni up, Ni down, sum over all sites. So of course, for fermions, we can only have two fermions on the same site when there's spin up and down fermion, right? We can't put two spin ups from Pauli principle there. So this is a little bit different than in the both Hubbard, but they both follow directly from that. That's the only steps you have to do. There are actually a few more terms that come out that I'm sweeping under the rug. If you really want to be careful, you have to also think about those terms, but those are the dominant terms, the most important terms that we have. And it's very nice what they describe actually. Then I can come to your question. So think of this lattice. And now you just have particles which can hop from one side to the next. They're all in the lowest band. And when two of these particles come together, for example, a spin up and a spin down, their energy is shifted by an amount U. And this U basically is just proportional to the scattering length and how tightly we confine these particles on site together. So I've written the formula down in the notes for you, so you have that. Okay. All right. There were a few questions I see. Yes, one. Yes, good question. That will be determined by the total angular momentum of the atom. And that means it really matters what kind of isotope you're using. So you can use, for example, potassium-40. That's a fermionic isotope with an odd half number of spin. And then you can use potassium-39, which has integer spin, total angular momentum, which is a boson. So just switching from one isotope to the next allows you to switch between boson or fermion. That's nice also. And actually the fact that we can work with fermion, I think, is a tremendous benefit of this platform, because compared to everybody else, I think the only other community that does that is quantum dots, community. This is very nice because, of course, simulating strongly correlated electron physics is one of the motivations of doing all this, being able to do this direct overhead of mapping your spin problem, your electron problem onto the spin problem. You can directly use the fermions. Yeah, very good question.
Sorry,
yes.
It looks like you only have now one state per side, but the picture you draw on that board has something like 3 states per side.
Yes, very good question. So these are basically h bar omega vibrational, away, and we're just considering a case where our interaction energy is smaller than this, much smaller than the vibrational energy, and we've cooled the particles down. They only are in the lowest band. So this orbital, what people call orbital physics, also very interesting when you talk about these higher bands, but we don't want to talk about it in this lecture. Okay, so we try to be in the lowest band by starting with initializing the system in the lowest energy state and having interactions which are actually smaller U than the energy band splitting, so we don't have to worry about that problem. Okay. All right. Yes. Absolutely. Yes, yes. And you're absolutely right. The hopping, if you, for example, if you are here and you want to hop, or if you are here with this wave function, because this is much broader, this wave function is a much larger overlap with this one over here. Typically, the tunneling rate in the first band is a factor almost 50 to 100 larger than in the lowest band. You're completely right, but of course, there are other things. Interactions are, of course, strongest because there the wave function is most confined because we have this delta function interactions. You want to confine the atom strongly, so there, for that reason, you favor, from the interaction point of view, you favor actually being in the lowest band. And you're completely right. That's why what we always have to do, we have to think about making the shortest spaced lattices that we can. We can't do what with tweezers, you can forget it. Tweezers, you have separation of 5 micron. There's absolutely zero time coupling from one tweezer to the next. They just don't hop. Well, at the age of the universe, maybe, but that's beyond any PhD student expectation. Yes. Yes. Omega, you mean the 2-level system here? Yeah, well, that's typically an optical frequency. That's the 2-level system. I'm talking the parameters here for the lattice. I'll give you in a second on the slides. I'll show you in a second what parameters we're dealing with. Actually, we can do it now already. Okay, so yeah, so let's look at a beautiful lattice. Let me show you one. Take nice Leo stick. So we are dealing, we're putting atoms in there. They have different hyperfine states. If we pick 2, this can be our spin up and down states of the electrons, for example. Or if you're in GILA, you like to work with optical clocks, then you can also use an optical transition and realize qubit states spin up and down on optical transitions. And all that stuff is loaded into this lattice. This is a beautiful one. This is one from Ted Hensch. This is the quasi-crystal structure that is made by interfering 5 laser beams. And that's not the Mathematica plot. That's the real interference pattern recorded with the camera. Okay, you really see how beautiful it is and how defect-free it is, and how nicely we can control that. Okay, so we can put thousands of particles in these lattices, and that's the goal of trying to understand what we do in these systems. All right. Yeah, since you've asked the question, let's quickly go through the numbers. So this is the lattice. The separation, since we're working with optical wavelengths, are typically between 250 nanometers and a micrometer on the spatial scale. On the local vibrational states here, the wave packets are confined to 10 nanometers to 100 nanometers with vibrational splittings between 10 kilohertz and 1 megahertz, depending on how deep you make the lattice, how much money you have to buy a powerful laser. Okay, we like to have very powerful lasers in the lab. And then you have the tunnel coupling between sites. This was also a question that was asked, how strong is that? That's actually around between 100 hertz and 5 kilohertz typically for the systems we look at. Okay. Okie dokie. Yeah, just a question, just let me show you this. One thing is nice that, very recently we found a way how we can synthesize all of these different lattice types in one geometry without having to change the interfering laser beam pattern. I wanted to explain how we do that, but seeing that we have much more interesting stuff maybe to discuss, I'll just skip that and just keep in mind that, by basically you can realize all these different structures: square lattice, hexagonal lattice, triangular lattice, Kagome lattice, leap lattice, basically in one experimental setup now. Okay, without having to reshine the laser beam. All of them are super interesting for different reasons. This one, if you want to have frustration effects. Deep lattice is very interesting when you think about twisted bilayer graphene, because it's actually one of the simplest configurations that mimics what you see in bilayer graphene. It has a flat band in the middle, and the flat band is not due to trivial flat band physics in the system, because also frustration effects. So all these are interesting, and you can change between them. Questions? Very good. You're a good crowd. You're very interactive. Very good. Yes. 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 So this one was indeed made by 5 laser beams. Indeed. Yeah. So we'll skip that. Just to show you, I can also do zigzag ladders if you're interested in that from a theory point of view. That's also very nice, often what you want to have. So all that's possible basically in the experiment. Yeah, so U can be between a few hundred hertz to kilohertz. So and that's what I want to talk about next. Actually, what is now, if we look at the phases that arise. Yeah, you're just, are we good with the speed, or is it too slow? Is it all you know everything? And if you know all the stuff, please also tell me, then we can just skip forward a bit. But if you're happy, we just keep the speed and you keep asking questions. All right, now this both Hubbard and Fermi-Hubbard model get very interesting when the interaction over the kinetic energy becomes much larger compared to one, because then interactions really dominate the behavior of the physics. And Matthew, of course, played a very important role in elucidating what happens in the case of bosons, and this kickstarted my own career. So I'm very attached to this U over T large against large compared to one regime here. And it's of course also important for the strongly correlated electron physics. And so let's imagine this case repulsive interactions, and let's imagine N is basically 1, the filling. Then we have different interesting physics that appears in the charge sector. And pardon me, I often speak charge, but what I actually mean is density. It's just the language that a condensed matter physicist would use, because there you're dealing with electrons, and whenever you think about electrons, you think about charge. For us, neutral atoms, they don't have any charge, right? They're neutral. But so we should just replace in your mind charge by density, charge sector. If we cool down the system in this regime for strong interactions to temperatures much smaller than the interaction energy, then what we get are these so-called Mott insulators, where basically particle number fluctuations become extremely costly, and you really want to order in Fock space in really localized particles with distinct occupations per lattice size. So you really want to go in this extreme limit to a case where you would have Fock states with exactly 1 atom per lattice site for the case of the single component bosons, for example. This has a finite gap, the system. We have suppressed density fluctuations. And yeah, maybe that's all I want to say for now. In the spin sector, if we do this with fermions, there's also for repulsive interactions, if we cool to temperatures actually below what we're going to derive now, smaller than the exchange coupling in the system, then we're going to see that these fermions actually want to become a Heisenberg antiferromagnet. And I'll also show you pictures of that, how we can see that in the experiment, this Heisenberg antiferromagnetic ordering. And then the whole interest of strongly correlated electron physics, which is not topic of this course here, is of course what happens when you whole dope or particle dope these systems to understand what the interaction of these dopants with the antiferromagnetic background is. It's the key question people are trying to understand. So whole doped system and the interaction with antiferromagnetic background. Okay. All right, so where does this come from? Why do they want to order antiferromagnetically? And the mechanism for that is, of course, super exchange. And I just draw it here in a picture, cartoon picture on a double well cartoon. I like the double well. It's really beautiful to understand a lot of the physics we're talking about. So imagine you are in a situation where you have suppressed density fluctuations. And so you have 1 fermion here, 1 fermion here, and you would have 1 spin up and 1 spin down. Then obviously, if this particle hops onto this side, you would have 2 fermions here. But that state has strong repulsive energy, right? It has a different energy. This one has no interaction energy. This one has interaction energy U. So it's energy U above this state. So you cannot stay there because it's, would violate energy conservation. So you have to go back, and you can either then go back to the original state, or you flip the 2 spins, which you can also do. Now, how strong is this process? Well, this we can just calculate with second order perturbation theory. We have an amplitude of going from here to here, T, another single hopping event from going here to here. And of course, we could have also placed the 2 particles to the left, and it would have been the same story, okay? And this gives rise then to an effective coupling between those 2 states, which is just J exchange, which is just 4T squared divided by U. Okay, so that's how you get a spin model out of this Hubbard model, where you can now basically write down an effective spin model in the case of unit filling minus plus J exchange sum Si Sj over the nearest neighbor sites, you've made out of your Hubbard model in the regime of strong interactions and half-thing. You've made a spin model where in the case of fermions, the model is antiferromagnetic, whereas in the case of bosons, you have ferromagnetic. And the difference just comes from this simple exchange sign. When you switch, the two positions between the two, in one case for the fermions, you pick up a minus sign, in the bosons you don't. And that makes the coupling ferromagnetic or antiferromagnetic. Okay, very good. What is nice, there are several ways to tune this that I want to mention. There are a couple of ways how we can tune this J exchange. So it turns out if you generalize this formula, for example, in the case of two-component bosons that you would have, turns out you can basically generalize this and you can basically get to a fully tunable XXZ interaction where you can basically tune, for example, the different interaction strengths of bosons U up, U up down, and U down down. Or you could also have cases where the tunneling for the different spin components might not be the same. So that's what we call spin-dependent potential. If you have that in the bag or one of these components, then out of this model, you can deform it into any XXZ model you're interested in. Okay? You all know, should I say something about this XXZ model, or you're all super familiar with this XXZ model? So the XX coupling is like a kinetic energy, and the ZZ part is like an interaction part between the spins. All right. Yes. So what are you asking in the spin model? If the oh, well, okay, this this you can do. If you have tuned Feshbach resonances that would make U up, down, or U down, down different. I've put the paper in the notes so you can look it up if you're interested in learning about that. If you want to have different coupling strengths in the different dimensions, that's very easy. Then you can just make the lattice weaker or deeper in one dimension, and that will enhance or ameliorate the exchange coupling in that direction. Because remember, the exchange coupling is like 4 times T over U. So if you make T smaller, right, in one direction, that would also mean the super exchange in that direction will be smaller. So you can make it anisotropic. You can make it fully isotropic in 2D. You can also decouple chains and make it fully 1D. That's all possible. And you can deform the model to become a general XXZ model with these tuning knobs. Yes. So this would be when we have 2-component bosons. You're completely right. For just spin polarized bosons, there would be no such thing here. This is the case if you also have 2-component bosons, a spin up and a spin down boson, and they would then show a ferromagnetic coupling instead of antiferromagnetic coupling for the fermions. Okay? Yes. Yeah, because there will be different ways, well, for the bosons, you can do that. For the bosons, you can tune that because they're again like different pathways. For the bosons, you can also have up hopping onto one side, which is forbidden for the fermion case. So, okay, I think I just have to refer you to the paper by Anatoly Kuklov and Boris Svistunov where this is derived. It's in the notes, so I cited it there and you can look it up. I think for the course, the only thing you need to remember for now, I think, is that you can make this tunable, and it has been used. Wolfgang Ketterle used this a lot to make tunable XXZ models, for example, because he has lithium with nice Feshbach resonances where all this is possible. Okay. No, Heisenberg would be for fermions, antiferromagnetic Heisenberg. For bosons, you can get ferromagnetic Heisenberg or any XXZ variation you want. Okay. All right. Okay. Then I want to talk about Rydbergs briefly. You heard that. In principle, you should know that. So again, tell me if you know it. I'm just going to do it again. It doesn't matter. So, you know, learning is an experience of repetition, right? Repeating things and understanding things again. Okay. So,
I suggest just using little larger font.
yes, I'll try that. So hard for me. You need larger blackboards here.
Huh?
You need larger blackboards here. Yeah, there's another one behind this I think I could use, but I can also use that. Yeah. Yeah, maybe we can start with that one and then we'll clean up a bit. Oh yeah, very nice. Good. Okay, then. So this is collisional interactions. We understand what we should have taken from this now is what is the collisional interaction based on? How do we derive Fermi-Hubbard Bose-Hubbard model? How do, in the regime of strong interactions, spin models come from that? And you know, what kind of spin models can we have? And what are the typical scales? So that's what you should know for now. Now I want to explain what we can have more or different with Rydberg interactions. So again, I want to do a very simple model for that. So we consider two atoms, atom 1, atom 2. Each of them has a dipole associated with them. And we now want to think of the dipole-dipole interaction between these atoms at a certain distance r between them. Okay. So how can we write it down? Well, we can just think of the dipole-dipole operator, which would just be d1, d2 minus 3 d1 projected onto the inter-atom axis connecting the two divided by r cubed. Okay. So that's a general form of the dipole-dipole interaction between these dipoles. And we're going to simplify. There's this, of course, now you see there's an anisotropy here when dipoles are aligned like this in the plane, they repel each other. And they're like this, they attract each other. We don't want to, that complicates the mathematics a bit. And we don't want to, I don't want that right now because it obscures the physics. I want to stay with the simple derivation of the essential physics. So what we're going to assume is that these dipoles are aligned to each other, and we're just going to consider the cases where they are aligned and we and perpendicular to the internuclear axis. Okay, so we assume poles aligned and perpendicular to the internuclear axis. And then the V of R, the internuclear potential that you get would just be something like norm d squared, where this would be the typical dipole-dipole interaction matrix element divided by 4 pi epsilon naught r cubed. Okay, and that's all we need to use from now on. And it just makes things a lot simpler in the interaction. All right, so let's consider two atoms. There are two, each of those atoms has two very excited, highly excited Rydberg states. Let's call one of these Rydberg states I, and maybe an S state, and then there's a P state above. Let's call that J. And this is our atom 1. This is the atom 2. In this case, and now I want to write down the coupling matrix, the Hamiltonian, of this dipole-dipole operator, of these pair states. Okay, so there were going to be 4 states in here. There's going to be the 4 states that we have to include where both atoms are in the ground in this lower Rydberg state. One where both are in the excited state, and these states where one of them is in the excited state or the other one is in the excited state. Okay, so these are the 4 pair states that I have to include. And with those and the VDD, we can explain everything in the Rydberg physics. Okay, so that's what we're going to do next. Yes. Yes, this would be well, this could be an S state and this would be a P state, for example. But it could also be a P state and a D state, something that's allowed by dipole transition. I'll come to that. That's all in here too. Just back with me, it's all in this one, and which in this 4x4 matrix. That's all going to come out. Both the resonant Rydberg interaction and the van der Waals ZZ interaction. Sorry? If you're in the I state, in the eigenstate, But while I have to the couple, if I'm in state, the matrix element IJ with V is not 0, and that's the crucial point. Right? And let's say there's an energy difference. Let's call this H bar delta, this energy difference between the 2 states. Okay, so let's write down the coupling matrix of VDD in these 4 basis states. This better now from the size? Are you getting? All right, yeah, you just keep pushing me. That's good. So we have II. Sorry, they have to be small here, and but to get it, IJ. JI and JJ, and the same thing here, II, IJ, JI, JJ. So now let's think about the diagonal elements. Well, if both are II, that's our, let's say, the reference ground state that has energy 0. If one of them is in excited state, then we have H bar delta. So this one has H bar delta, this one has H bar delta. And this one, both are in the excited states, you have 2 H bar delta. Okay, good. Now, what about the coupling matrix elements? Well, we can go, these are coupled by V, going from IJ to JI. And the same thing is also true here for the II and JJ, they also have that. And all the other matrix elements are 0. Because of parity reasons. That's it. And everything, and now you can already see that you basically have a structure where if you're in this subspace, you have a 2x2 Hamiltonian. And if you're in this subspace, you also have a 2x2 Hamiltonian. This one we'll see is the resonant dipole-dipole interaction, gives a 1/r³ interaction. This one is the one which gives us the 6 van der Waals 1/r6 interaction. All right. Okay, let's start and do that. Yes. Yeah, in principle it could be different, but we don't want to discuss. We don't. Yes. Again, I just try to not cover the maths. I try to make the formula as simple as possible. All right, so let's look at direct exchange, what we call direct exchange. That's the state where, for example, you start out with one of the atoms being in the ground state, the second one in the excited state, and then you can immediately see these are resonantly coupled because they have the same energy with this energy E to each other. So they are resonantly coupled. If they're resonantly coupled, we know that the eigenstates of this 2x2 Hamiltonian are just 1/√2 ij plus ji and ij minus ji, the symmetric and antisymmetric pair state combinations, right? And that means that, of course, you're going to get resonant exchange at that frequency, and that's why we call this the direct exchange. If we look at the energy of these states as a function of R, then these eigenstates would be one of them is the symmetric state, ij plus ji, and one is the antisymmetric state, and this one goes like this, and this one goes like this with distance, and this coefficient would be just a matrix element, which is just the dipole operator squared that we have there, the dipole divided by r cubed, because that's the V. Remember the V I had over here, the V of R is just the d squared over r cubed interaction. So one shifts up and one shifts down in energy. And this is just minus d squared over r cubed. And that's what we call the resonant dipole exchange. Okay, if you start in one of these states, it's not an eigenstate of the system, the superposition is, and therefore you get resonant exchange at a oscillation frequency, which is just given by your d squared over r cubed. So you see, the closer you bring the atoms together, the stronger, of course, this interaction becomes. That's direct exchange. All right? Yes? That can be because you have the dipole operator can also connect you there. Those states in pairwise they connect each other. There's a non-zero matrix element between them. All right, now I need to clean something. Give me a second. Where's the? Ooh, this is a massive thing here. Bring this over. Sorry.
Not dry in time.
It will. I'm experienced. I do this all the time. With the other one, it will. I always wipe my board clean. It's always so nice to have a clean blackboard. No, I hate it when you have the blackboard and it's all just white and you can't read anything anymore. All right, so now we want to discuss this other regime, which is the van der Waals regime, which is this other 2x2 coupling matrix that you have in here. So if we write down just the van der Waals Hamiltonian, this would be between the states II and JJ. And there we had this 0 to H bar delta BV, right? So this is this other part of the Hamiltonian that we had if we go to the II and JJ states. And now again for V, let's say, is typically smaller than this 2H bar delta, we can treat this. We could again just diagonalize it and get the formulas, but actually it's easier just to see the physics with second order perturbation theory. So I remind you again, my corrected energies to second order will be the original energies, the pair energies plus I VI. If I label these states, these single particle states or some generic state. This one would be 0 for parity reasons. And then I have here this sum I unequal to J. J V I squared divided by EI minus EJ. Right, and the state vector is corrected to first order. That's just my original state vector that I have, plus sum I unequal to J, JVI divided by EI minus EJ, J. Okay, so what does that mean? Let's draw our picture. So we have the state JJ, both atoms in the excited state. We have the state II, both atoms in the ground state. Now we turn on this dipole-dipole coupling, where I can basically make virtual transitions to this JJ state, then have to go back. This will lead to an energy shift of these levels, which we just calculated. That's our second order perturbation theory result, which we can now plug in the dipole operator in the pair states. And if we calculate, you see here, what goes in is the dipole operator squared. The dipole operator was d squared over r cubed. So now we're going to get something d4 over r6, and that's where the r6 comes from. okay, the van der Waals interaction comes from. So this is going to be one moment. I saw your question. Let me just write this down. So this is V squared over 2 h bar delta, and also the energy difference for the C6, the energy difference between the states matters. This energy difference is 2 h bar delta. And here it's going to be just shifted down by the same amount, minus V squared over 2 h bar delta. Okay. And the states, the eigenstates are going to be modified eigenstates. The JJ is going to get a little bit of amplitude of the II state, and the II is going to get a little bit of amplitude of the JJ state, the new modified eigenstates. All right. Right, so what's this? Let's look at this. I have to clean something more. This V squared over 2 h bar delta. That's basically the dipole operator squared to r cubed. That thing squared divided by 2 h bar delta. And that is what we call T6 divided by R6. So, oh, sorry, the 6 has to go. Apologies. The 6 coefficient is just all the numbers. So it depends on the dipole matrix element 4, the energy separation of those states that goes in there. But in general, we have the 1 over R6 contribution. So that's the interaction you get when you are starting with both atoms in the ground state. You're going to get an interaction, a van der Waals interaction. Talk about what of the course, the strength of the van der Waals interaction. Now, just one quick comment. Remember our Born-Oppenheimer potential that I drew you. There's also a C6 divided by R6 here. It also comes from the same reason. It's the ground state. Now we don't have two Rydberg states. One atom in the electronic ground state coupling to an atom in the electronic excited state. So the delta is huge. It's an optical frequency. It's an optical frequency now. But the principle is exactly the same. The derivation is exactly the same. Also, and this always has to be attractive because in the ground state, the difference energy in the denominator is of course always negative in the ground state. So in the ground state, this always has to be attractive. In the excited state, not so. So this can be repulsive or attractive. That depends now on the details of your atomic physics. Okay. Yes. Well, what it means if you stay, okay, let's do it. Let's start in state ij. Oops. This one doesn't move. Okay. Okay, I go down. If you start in ij, that is a superposition of the symmetric state minus the antisymmetric state. No? Let me call this the symmetric state and this the antisymmetric state. So now these are not degenerate in energy because they are split in energy by this d squared over r cubed interaction. So they're going to evolve at different phases, and that means eventually if you calculate the point where the phase shift between them is exactly pi, this is where this state with a phase shift of pi has gone over into the state ji. So it really means the following. Physically, I'm running out of options here. Is there another one up there? Yeah, I think we really need to clean this now. Okay, let me draw here. If you start in the following configuration, let's imagine you have two atoms next to each other. Okay? Okay, there you are. One is in the excited state, one is in the ground state. So this is state I, remember this is state J. So this would be the state Ji. Okay. That means after a half exchange period, it will have moved to this state, where this one will be in the excited state and this one will be in the ground state. But the excitation has been exchanged between the two atoms. It's a flip-flop interaction. Or if we now already go a little bit forward in terms of spin models, it's an XY interaction, which is exactly what does that, S plus S minus, a swap interaction. And the rate at which they swap the excitation, that's given by the dipole, resonant dipole interaction energy, d squared over r cubed.
You can also think of any side of the plane wave, something like this. But if you only have two sides, you have only two wave vectors. One is k equals 0 and one is k equals 0.
Did that help you, or is it? Yeah. All right. Good.
Anyway, just to be clear, there's because it's d squared that appears.
Yes. Yes.
That's non-zero even in the angular momentum eigenstate. Because it's d squared, isn't it?
I'm not sure what I understand exactly. You mean you're talking about which matrix elements are zero or non-zero?
So your direct interaction is goes as d squared over r cubed.
Yes.
No angular state don't have an average d. D squared is non-zero. So in principle, there's a diagonal pieces that are shifting.
Exactly.
And maybe they're shifting differently in the S and P.
That could be. I'm all sweeping that under the rug. Yes. Yeah. I just want to boil this down to the absolute, essential physics, and there can be a lot of details in that. Because I believe, but maybe I'm wrong, that most of you don't have an AMO background, and I just don't want to obscure the physics with the AMO. There's things are usually harder in practice, but you all know that. And what I try to do is bring it down to a level, what is the essential physics that goes into this? Okay, and yes, we of course should have to take the full dipole operator like in the beginning. Yes.
Okay, so maybe that. Well, okay, so that's what I'm asking. You think it's zero because they're on different sides.
Okay, very good. I have to think. You're putting me under pressure here in the course. Okay, yes. That's parity. You mean IJ to II? That's parity forbidden. That's forbidden by parity rules. Okay, let's put the summary. Now let me summarize everything I told you in one graph to see how these states shift. So let's write here at the energy axis. We have, let's say, what we call the lowest energy state is where both atoms are in state II. Pair state is II. And we have large distances. Here's R. And for very large distances, of course, the dipole interaction does not play any role. It falls off like one of R cubed, so it's like independent atoms. So for very large distances, we have the JJ. This state has which energy? Has energy 2 h bar delta. This one has energy 0. It's just what we do. And this one, where one of the atoms is excited, is h bar delta energy. And these are symmetric or antisymmetric states that are called plus or the minus states, which obviously become degenerate in the limit of R going to infinity. This one here goes like 1 over R cubed. This is what we call C3 over R cubed minus C3 over R cubed. And the pair states up here, they fall off much more quickly, like 1 over R to the 6th. So this would be R to the 6th and minus C6 divided by R to the 6th. Now remember how they bend, whether this one goes up or down, that really depends on the atomic physics. It's only certain for the ground state if we would be in the absolute ground state. So this could be the other way around, but I've just chosen one thing. So that's it. This plus minus gives us XY interaction, the flip-flop interaction. The II, the van der Waals interaction, which just gives us a SZ interaction, which I'm going to show you in a second. So this would be Ising interaction, swap X interaction, and we can now calculate the rates by knowing these C3 and C6 coefficients, and you know what the microscopic connection to the microscopic Hamiltonian parameters are. Okay. Good. Are we going too fast, or am I speeding up too much, or is it? Speed still okay? Again, you have to slow me down if I'm going too fast. Okay, yeah, then maybe the last thing I want to then talk about, how do we connect this to the spin models that you're interested in? Obviously, you know, this is all interesting atomic physics, but in the end, as a theoretician, most of you are, you just want to know, you know, and what am I going to get? What can I do then in these systems? So let me clean 2 boards, prepare for the final thing for today. Yeah, please. In the upper one also. Oops, I'm too small for that. Bad idea. Get to that one in a second. Okay, so let's go to the, say we want to implement an icing model. That, as I said, we can do with the van der Waals interaction. So here I draw my line again. We have the II, and or let's say, actually, no, let me call this now the true ground state, let's say, of my system, GG here, the absolute ground state. And then this would be my Rydberg state I. But I know my Rydberg state II, this one, is going to be shifted in energy. So that's going to be an energy shift, which depends on the distance. So fix the distance, it's going to be a fixed shift of that energy level. So that's going to be then the original state would be here. And now it's shifted in energy because of my C6 divided by R6 interaction in the system. So now what's the interaction term? When are we going to get this interaction shift? Well, whenever we excite both atoms to the Rydberg state, their state is going to be shifted by this amount. Right? So only when both atoms are in the Rydberg state are we going to get this energy shift. If we only excite one of the atoms to the Rydberg shift, the state will not shift. So we have to write down an operator which does that, and the operator that does that would be just C6 divided by R to the 6th N1, the density of Rydbergs of atom 1, and the density of having the second atom in the Rydberg state. So if the N operator counts if you're in the Rydberg state or not, the only time when this is non-zero is when both of them are 1. Right? When both atoms are excited to the Rydberg state, then we get this strong van der Waals shift. Now I can just write down an operator N, which would be just the identity plus sigma z operator divided by 2. And then you can see that this is basically nothing with an offset term like a sigma z interaction. Right? So if I put this N operator in here, you get a constant shift term. But then what matters for the interaction part is that you get this sigma z icing interaction, which you can now, of course, use to realize a phase gate between your atoms, and C naught if you put pi over 2 pulses in between, if you would have other hyperfine ground states involved in that. And one natural thing that I think probably Julia told you about, I'm sure she did, was in terms of interesting Hamiltonians that you can easily do is the transverse field icing model. Where you just combine this interaction part, the ZZ part, with the drive, so you have a Hamiltonian where you can now think of many of the atoms on a, let's say, trapped in the tweezers, we drive each of the atoms with a sigma X coupling of atom I. So this would be just Rabi, resonant Rabi coupling from state G to I on each atom. We just shine a laser that turns these ground state atoms into Rydberg atoms. Then we can have a longitude field if we go in frame. And then we have our Ising interaction part, which I again write in the density form, R6, Ni, and J. Okay, nice. And you can control all those parameters, right? You can control this one by spacing your atoms differently, making use of the R6 dependence. You can just choose different spacings, so you control the interaction. Changing the laser strength and ramp form, you can control the transverse field. And changing the detuning, you have control over the longitudinal field as well. And that has been really beautifully demonstrated by several groups, Antoine Brevet's group in Paris, Michal Lukin's group in Harvard, many, many others of the beautiful physics that you can do with this transverse field Ising model. And I'm not going to talk about that more because I'm sure Julia did a great job in explaining what you can do with this model. Yeah. Yes.
The delta term and the omega term, can you make that side dependent?
Yes, in principle, you can also do that by introducing laser beams that have a differential energy shift on the states. That's what Antoine did recently. So he basically had a staggered pattern because he wanted to realize an antiferromagnetic nail phase and connect that, adiabatically deform that. And to realize that, you have to shift on a checkerboard style every other side the energy level. And you can do that by shining a laser beam onto a specific site, which would shift the energy level of site I, for example, in a state-dependent way compared to the G state. Okay, so it should be something, a laser that doesn't affect the G state, but which shifts the I state. And if you then shine that atom, that beam on top of the tweezer beam on that site, it will introduce a localized shift. Yeah, and that actually was very nicely used to adiabatically connect this nail antiferromagnetic phase, where you basically start out by favoring that phase through this checkerboard style longitudinal tunings and connecting that to some interesting long range XY phases with the dipole interaction. So it's very nice work, just very recent work, I think just a few months ago in Nature. Yes.
What is that the longitude to 0? Is it difficult to tune delta to cancel the part from the term?
Yeah, that's a good point. That's always, yeah, the questions, can you really be delta to 0? Because in principle here, there's an offset term coming in also. That has made me wonder also. I think in principle you can, but it could have other effects where, for example, at the edge of the system, you have a different detuning because this offset term is different than in the center of the system. So it's not homogeneous anymore, and that can influence the dynamics of the system. And I always worry about this too, and I don't sure I have an exact answer to this.
I guess you just said that you use delta in a site-dependent way.
Well, then you could cancel it for sure. But let's say if you don't do that, then indeed at the border of the system, because this term will generate an detuning, but if you're in the bulk, that's going to be the same everywhere here, but at the boundary, it's going to be different. And that could mean that as you change parameters, you preferentially start doing things on the boundary and then coupling into the bulk. And okay, that has worried me too. I don't have a good answer to that. I didn't think about it deeply enough, maybe. Yes. Where does that come from? Just a laser that we shine from G to I. So remember, we think about it like this. We have an atom here, an atom here, an atom here. They're all trapped in these tweezers, okay? Each of them are two-level systems where we can have state G and state I. And now we just shine a laser beam, let's say a global laser beam, onto all of those atoms, which couples state G and state I. That's a different, yeah, because this is an external laser that just does single qubit rotations. It's just a laser that connects state G and I. The other one was dipole-dipole interaction, which basically did not allow me to couple those states directly to each other. The pair states, remember, those are the pair states we're talking about. But here I'm just talking about, let's say, a ground state S to P transition, a dipole allowed transition, where I can just shine in my laser and it's allowed transition. Okay, and then I just have this omega is just the Rabi frequency of my laser beam that I shine onto that site. So in principle, that could also be site dependent. If you shine thousands of laser beams onto the different sites, that can all be tuned individually. I'm not even assuming that. Most of the time you have global. Okay. All right. Final thing. Let's just look at XY. Look at the XY. Oops. Yeah, now I'm in the mode which I didn't want to be, this nasty blackboard, which is white. Okay, so implementation of XY model. So that we can basically just do with the resonant term, where we know that the Hamiltonian for the resonant dipole-dipole interaction, that was just C3 divided by R cubed. And then it just exchanged ij to ji. Well, in terms of operator language, that's just sum over all the neighboring sites, or the ones that were within range, S plus, S minus, I j, plus S minus, I S j plus. Right, so this does exactly this flip-flop, what we talked about. It takes the spin here, flips it down, and flips the spin on the neighboring side j up. And the strength of that, that's just given by this Rij, the distance between the atoms, how strong that is. Okay, and that's how you can do just a pure flip-flop interaction. And tomorrow, maybe we'll talk about how we can use Floquet techniques to combine SZ and XY to make anything you want XXZ. Okay, but now you know the basic ingredients. Resonant exchange, XY, van der Waals giving us the sigma C icing interaction. Anusha. Yeah, so you have to watch out. Typically, the C6 is much smaller than this one, the resonant exchange. That's a good question. So if you have neighboring atoms, if you had two atoms that would be close to each other, you would have to take the residual van der Waals interaction into account that they can have. Typically, it's so much shorter. So what people typically do, Antoine, for example, has done a lot of work on this XY Hamiltonian, XY model, because you can write this as XX, SXX, and SYY terms. You typically go to very large distances where this is still very strong, but the van der Waals has become negligible. So he works at rather large distances. I'm not sure right now of tens of micrometer, whereas typically for icing type experiments, you would go on the scale of a few micrometer, 5 micrometer typically. And remember, it goes like R6, so it's a big thing. You go a factor of 2 or 3 more, you win. You suppress that interaction a lot, actually. All right. Yes. Well, there you just have to make sure, there's not, well, you have to watch out. Maybe I confused you. This is not the J. So this is the II, and then there's another JJ up here, and you never go there. The JJ would be up here. Okay, and you don't go there. But you're touching upon a very important point. Let me tell you what is catastrophic for Rydbergs. Black body radiation. If you are up here in the I state and a black body photon comes and takes you to the J state, now suddenly you're opening up that manifold, because if now the neighboring atom is excited to I and the other one is in J, then you get the very strong resonant dipole-dipole interaction. So black body can be super detrimental and have catastrophic effects, like even really avalanche type effects, what this does to the system. If you have a single excitation, single decay into the wrong state, which suddenly facilitates strong R-cubed resonant dipole exchange interactions, that can be catastrophic. So you really want to avoid that. And that's one motivation why eventually, I think for all these tweezer experiments, they will want to go cryogenic. That's one reason. Or put a Faraday cage around it. You know, could also think these are microwave frequencies. You can also make a Faraday box and try to make a cavity that keeps the radiation out. Yeah, we think so. We think so. We did some calculations. We'll say from the calculations, yes, but you know, we have to try that. So that would be a nice solution. But I mean, there are other reasons why you want to go to cryogenic, and that more practical reason is also why, because the vacuum lifetime increases dramatically. But okay, this is so much more technical, but vacuum is such a big topic for an experimental physicist that you know you don't even want to hear about it as a theorist. It's usually just problems. Okay. This can depend. So whether this is positive or negative, this depends on the atomic physics. This C6 only in the ground state can we absolutely be sure that this is negative. This really depends how close is the P state above the S state or below. Is your J state above the state or below the I? So is this detuning positive or negative? As we said, this determines now, of course, whether this can be positive or negative. And there's this, if you want to try it out, you can go to the web. There's this beautiful page from Hans-Peter Büchler in Stuttgart. They set it up, pair interaction, it's called. And you can calculate all the Rydberg pair interaction potentials. And you get hundreds of lines. And it's not so simple, you know, as I try to explain. But they take all that into account. And you can then see the correct, calculate the correct C6 and C cube coefficients. But I think you got the main message, what this depends on here in a two-level system. Leo.
Do you have, how do you generate ZZ?
Well, you have to couple to this. How you can do it with some flocatrix. I'll tell about that tomorrow.
Natural.
Yeah, natural. That's the natural. What natural thing? What we have is either XY, non-interacting, or ZZ icing. And by the way, that's the same also for the molecules, but for polar molecules, but there the ZZ is even much smaller. So the flip-flop is the dominant. The XY for polar molecules is the most relevant one. All right, I'm exhausted. So if you're not, that's it for today. Thank you. Thank you.
Quick reminder after the next lecture.